Let's explore the journey from multi-agent systems to the development of production-level LLM agents with Antonio de Castro. Antonio de Castro, a PhD in Informatics Engineering, shares his expertise in AI, multi-agent systems, reinforcement learning, and optimization, highlighting his work on multi-agent systems for airline disruption management. Today's journey will cover the essentials of agentic AI, from its definition to future directions, including frameworks, challenges, and industry applications. Agentic AI moves beyond chatbots, creating systems that can plan, act, and learn autonomously. Agentic AI systems perceive their environment, reason about goals, act through tools, and iterate with minimal human intervention until tasks are complete. The core components of an agentic architecture include the brain, tools, memory, and environment, working together seamlessly. The autonomy spectrum ranges from scripted automation to fully autonomous systems, with most production systems currently between tool-using agents and multi-step planners. LLMs have revolutionized AI by shifting from symbolic to probabilistic reasoning at scale, enabling more flexible and powerful systems. Before LLMs, AI relied on hard-coded reasoning and fixed schemas. Now, LLMs enable flexible, schema-free understanding and rapid deployment of new behaviors. LLMs serve as universal reasoning engines, supporting structured output, function calls, and in-context learning, making them the core of modern AI systems. Classical multi-agent system concepts are reimagined in modern agentic AI, leveraging LLMs for enhanced reasoning and planning. Concepts like BDI architecture, agent communication language, and Blackboard architecture from classical multi-agent systems are directly applied in modern agentic AI. Compare Jade and LangGraph to understand the evolution from classical multi-agent systems to modern agentic AI, focusing on flexibility and integration. Agent communication has evolved from formal structured to flexible, natural language-based tool calling, enhancing interaction capabilities. Modern agentic AI integrates classical multi-agent systems research with Gen AI, enhancing autonomy, reasoning, and coordination capabilities. On the anatomy of an agentic system, we explore the internal workings of a production LLM agent, focusing on its core components and capabilities. The core components of an agentic system include the agent core, tool layer, memory layer, orchestration, and observability, each playing a crucial role. The React pattern is fundamental to LLM agents, involving a loop of thinking, acting, observing, and reflecting to complete tasks. LLM agents use tools like web search, code execution, and database access to perform tasks, acting as the hands of the agent. Memory systems in agents include working, episodic, semantic, and procedural memory, enabling them to remember and learn from experiences. Retrieval-augmented agents connect queries to domain knowledge seamlessly, enhancing responses without retraining. Let's dive into the world of planning, reasoning, and multi-agent systems, transitioning from single-agent loops to complex networks. The chain-of-thought reasoning technique enables the LLM to think step by step. React, plan and execute, and generation and reflection are methods for LLM agents that rely on this technique. These are the architectural pattern FEUP diagrams for the React and plan and execute patterns, showcasing reasoning and execution flows. And here we have the explore generation and reflection and tree of thought patterns, focusing on generation, critique, and reasoning paths. Regarding multi-agent orchestration patterns, there are three main ones: supervisor, pipeline, and collaborative, each with unique coordination strategies. LangGraph proposed some multi-agent patterns. Here we have the sub-agents and handoffs patterns for specialized tasks. And here the explore skills and router patterns, showcasing dynamic context loading and task distribution. Finally, it is possible to create custom workflows, emphasizing deterministic control and validation gates. LangGraph allows to orchestrate agent workflows using graph-based models for efficient task management. Let's now look into the tools, stacks, and infrastructure ecosystem that supports the production of agentic AI systems. The modern agentic AI stack goes from application, orchestration, memory, and storage to observability layers. The hard truth is that the majority of agentic AI engineering is infrastructure, not prompting. This fact emphasizes the importance of robust engineering over simple prompting. Let's uncover the challenges and failures in production, focusing on what demos often overlook. Look at the gap between demo and production environments, highlighting unexpected inputs and real-world complexities. The hardest part is the evaluation of agent performance, from task completion to latency and cost. Common failure modes in agent systems goes from infinite loops to state corruption, hallucination, prompt injection, context poisoning, and cost explosion. Controlled autonomy in agent systems is achieved by focusing on human-in-the-loop checkpoints and protocols. Let's look now into an industry case study on airline disruption management, transitioning from classical multi-agent systems to LLM agents. The multi-agent system for disruption management manages airline disruptions using multi-agent systems, optimizing aircraft, crew, and passenger recovery. The evolution from classical multi-agent systems to LLM-based systems marks a significant shift in how we approach multi-agent systems. Initially, classical MAS relied on symbolic planning and deterministic solvers, but faced limitations in adaptability and interface. The transition to LLM-based systems has introduced more flexible, language-oriented reasoning, transforming constraints into tools rather than obstacles. The architecture evolution from v1.0 to v3.0 showcases the transformation in system design. Starting with operational events and classical MAS, the architecture has evolved to incorporate constraint solvers and optimization engines, leading to the current LLM orchestration and solution evaluation. The architecture deep dive reveals the intricate orchestration of disruption events in real time. The disruption orchestrator coordinates various recovery agents, ensuring efficient handling of crew, aircraft, and passenger care, supported by constraint solvers and notification tools. Key lessons from the trenches emphasize the importance of keeping classical solvers as tools, prioritizing design evaluation, and recognizing the non-negotiable nature of observability. Human-in-the-loop systems and latency considerations are crucial for real-time operations. The future of agentic systems is a promising frontier where research and industry are converging. This section explores the potential directions and innovations that lie ahead. In the near term, advancements in AI evaluations and reliability are expected, with multi-model orchestration and faster inference. Long-term AI operating systems will feature self-improving agents, embodied robotics, and agent societies, all governed by robust frameworks. Agent societies and the multi-agent system research revival highlight the ongoing importance of coordination protocols, emergent behavior, and interoperability. Security, trust, and governance remain critical as multi-agent systems evolve with LLMs. As agents. Now let's discuss agents, multi-agent systems, production AI, and anything from today's talk, considering the key takeaways. Modern agentic AI systems are re-implemented with LLMs, emphasizing the importance of evaluation, observability, and reliability.